Well, hello everyone. We'll go ahead and get started. It's hard to believe that we're into the last week of our class, but it's been a wonderful journey and I look forward to finishing it with you all. So let's go ahead and open up in prayer and I'll give you a sense of the things that we'll be covering today. So dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course, Lord. I pray that the material has been clear and that they can have a chance to reflect back on the things that they've learned about computer architecture. Pray that this would be a helpful contribution for their future professions in the area that they would like to pursue. Also, pray that you would help them in their spiritual formation, Lord, that you would help them to get a better understanding of Scripture as they're getting the chance to take classes here at APU, and also for the times at chapel and other ways of experiencing the reality of our faith. Also, Lord, I pray that you would give them interesting and creative ways for faith integration, and pray that you would bless our time. In Jesus' name we pray. Amen. Okay, well, we're actually finishing up the material that we have installing, and I wanted to give a perspective of what we'll be talking part of our time on today, Tuesday, as well as Thursday. And so what we're going to be focusing on is this area called parallel organization of how can you have different computational elements working together collaboratively in a way that's going to help with the overall intent of a computing architecture. So up to this point, we've been talking mostly about a single computer. We have hinted a little bit about multi-core processing, and we'll talk about that on Thursday. But today we'll talk about parallel processing, and this will probably maybe take about the first half. And then I also want to allow some time for folks that they can be sharing their projects. And so I'll definitely leave some time for that. So let's go ahead and get into this chapter 20 that talks about parallel processing. And there's a lot of material that get into the various ways of how you can have a processing element collaborate with other processing elements. Since I've actually worked with cluster computers some, I'll point out this might be a way of getting your head around this. It's just some of this seems a little bit unclear. But I think if you look at some of the graphics that we have as a part of this chapter and pay attention to this high-level survey, and there's also a more detailed lecture that I've already provided to you that you can take advantage. So we'll talk about the multiple processor organizations. We'll talk about symmetric multiprocessors, the cache coherence, and there's something called the MISHI protocol. And so we'll get into a handful of charts that talk about that. One of the things that comes up when you have these multiprocessors and you want to take advantage of them, having multi-threading is one of the ways that you can be doing that. And so when you're working with cluster computers, you actually have to have a threaded version. Otherwise, it's used to just using one processor, one computer, and it can't take advantage of those. I know, like when I've used MATLAB, there has to be a cluster version of MATLAB that takes advantage of this parallel organization. And then we'll finish up with talking about memory access and how you can have non-uniform memory access. And that's going to get into the types of the architecture that you're dealing with. So in a broad sense, there are 4 classes of multiprocessor organizations versus the single instruction, single data, SD. So this is a single processor executes a single instruction stream to operate on data stored in a single memory. So uniprocessors fall into this category. So you can think like a desktop computer would easily fall into this. There's also the multi-instruction single data stream. So a sequence of data is transmitted to a set of processors, each of which executes a different instruction sequence. And it's not really commercially implemented. And so this gives you the taxonomy, but it's not really something we'll be talking about. And you'll see this in the next chart when I have a figure. There's also something called the single instruction multi-data stream. And so a single machine instruction controls the simultaneous execution of a number of processing elements on a lockstep basis. And so you can have like a higher level processing element controlling other sub-processing elements. And vector and array processors fall into this category. And finally, we have multiple instructions, multiple data. And this is a set of processors simultaneously executing different instructions sequences on different data sets. And then we'll talk about some of these subcategories that fall into this area. So this might be a clarifying figure to give you some perspective on these things. And so the SISD, you can think like the computer that you're using for this lecture would be an example of that. Then we have single instruction multi-data streams, and so we can have vector processor or array processors. We'll talk about that. The MISD isn't really applicable, so we don't see any branching on that. And then we have the multi-instruction multi-data streams, and the main two things is you have a shared memory, so they're tightly coupled. And so underneath that, we have the symmetric multiprocessor and the non-uniform memory access. And so this is one branch that we'll get a chance to talk about. And the other is distributed memory. And so you can have clusters. And so you could have a supercomputer, different computers that are optimized for that. You can have multiple desktops that you configure to work together in a joint fashion. And so this chart might be another way to give you some insight as what's going on with those different types of computer architectures or those organizations. And so first we have the SISD, so an individual computer processing whatever you're having it doing. And so that's probably fairly straightforward. Then we have an SIMD, so you can have a master controller that is actually causing all of these other processes with their own distributed memories all working together. So a processing unit in memory is following the instructions that are passed on from the control unit. So then we have two types of MIMD. And so this is where we have this division here. So the first is with a shared memory. And so here we see that they're all aggregating together. So a controller is just controlling the processing unit. And so we have N of those all with this huge shared memory that are being utilized. The other approach is we have some similar architectures to what we see in here. A control unit giving directions to the processing unit. It has its own memory. And then there's this interconnection fiber. And so all of these are networked together. And so this would be a good representation of what's going on for a cluster environment. So then we get into some more details about what some of this is. And so we have the symmetric multiprocessor. And so this is this part here that we had on this chart. And so it's a standalone computer with the following characteristics. There's two or more processors of comparable capability. The processors share the same memory and I/O facilities. All processors share access to I/O devices. All processors can perform the same functions, and hence they're the term symmetric. And the system is controlled by integrated operating system. So that's one possibility that we have. And then we want to be thinking about, well, we have these concepts of multi-programming and multi-processing. And so we can be doing interleaving multi-programming on one processor. And so this is, so we can have multiple processes that are taking place. And, or we can also have interleaving and overlapping. And so this is where we get into multi-processing with two processors or more. So those are some concepts that Stalling develops in the textbook. So this is a generic block diagram of a tightly coupled multiprocessor. And so there are two or more processors. Each processor is self-contained, including a control unit, ALU registers, and typically one or more levels of cache. And so all of these are networked together. So a processing element through this connection network engages with the I/O as well as engages with the main memory. So that's just a general diagram perspective of what's going on there. So with a symmetric multiprocessor organization, one of the main things that we see here is that there is a shared bus that's going on. So the time shared bus is the simplest mechanism for constructing a multiprocessor system. The structure and interfaces are basically the same as for the single processor system that uses a bus interconnection. The bus consists of control, address, and data lines to facilitate direct memory access transfers from I/O subsystems to processors. And there's a couple of features here that we can be thinking about. Addressing, arbitration, and time sharing. So for addressing, it must be possible to distinguish modules on the bus to determine the source and destination of the data. For arbitration, any I/O module can temporarily function as a master. A mechanism is provided to arbitrate competing requests for bus control using some sort of priority scheme. And then there's time sharing, where one module is controlling the bus, other modules are locked out and must, if necessary, suspend operation until bus access is achieved. So as is typical with stalling, he gives us a nice overview, and then he goes down a layer or two in having us getting some insight into this aspect of computer architecture that we explore one at a time. So this bus organization has several attractive features. It's simplicity, it's a simplest approach to multi-processor organization, flexibility, it's generally easy to expand the system by attaching more processors to the bus. And so this is seen a lot for, say, cluster computing that, well, if you just want to make a more powerful computational capability, you just add more processors, you add more computers. The reliability of the bus is essentially a passive medium, and the failure of any attached device should not cause failure of the whole system. And so we're seeing some redundancy and resiliency that's taking place. The main drawback is performance. All memory references pass through the common bus. Performance is limited by bus cycle time. Each processor should have cache memory, which reduces the number of bus accesses. It leads to problems with cache coherence. And so if a word is altered in one cache, it could conceivably invalidate a word in another cache. And you remember we did talk in detail about caching. And so you can have layers of cache. And so maybe one cache hasn't been totally synced, or something else that's going on that may cause some problems. This is typically addressed in hardware rather than the operating system. So just going back to a chart that shows this this taxonomy at a high level. So we're getting into this side, and I know I mentioned clusters when I was talking about this, but in this organization, they have a shared memory. And so we wanted to talk a little bit about the cache coherency problem that comes up with that. So we also have multiprocessor operating systems, design considerations. We need to be thinking about how we're going to be dealing with simultaneous concurrent processings. And so the operating system routines need to be re-entrant to allow several processors to execute the same code simultaneously. And the operating system tables and management structures must be managed properly to avoid deadlock or invalid operations. So we have to be figuring out how we're going to manage simultaneous concurrent processes. We have to be figuring out scheduling. If we're doing this, then we're not going to be doing something else. there's a limit to the amount of things that can be done in parallelization. We have to be thinking of synchronizations with multiple active processes, each having access to shared address space or I/O resources. Care must be taken to provide an effective synchronization method. We have to be thinking of how we're going to be utilizing the memory and also be aware of reliability and fault tolerance. All of those are things that need to be considered. So we have two types of cache coherency approaches. First is a software solution. So an attempt to avoid the need for additional hardware circuitry and logic by relying on the compiler and operating system to deal with a problem. So we can do a software-centric approach. It's attractive because the overhead of detecting potential problems is transferred from runtime to compile time, and the design complexity is transferred from hardware to software. But unfortunately, however, compile time software approaches generally must make conservative decisions, leading to inefficient cache utilization. So some good points and some bad points. We also could have a hardware-based solution. Especially with our project 3, you've got a chance to be thinking of a cyber physical environment. So am I going to have something that I'm going to have in my wiring board and do something that's hardware centric for a capability that you were trying to develop, or focus more on a software computer and then you just program the microcontroller, the Arduino? So generally, if we're doing a hardware-based solution, it generally refers to a cache coherence protocols. These solutions provide dynamic recognition at runtime of potential inconsistency conditions. And so there's more details here that we can get into. And there's a couple of categories that are suggested installing for the different types of protocols, either having a directory protocol or snooping type of protocols. So when we have some more details on those protocols and the directory protocol collects and maintains information about where copies of lines resist. Typically, there is a central controller that is part of the main memory controller and a directory that stores that is stored in main memory. And so there's more details there that you can get a chance to read over and installing. For the snooping protocol, they distribute the responsibility for maintaining cache coherency among all of the cache controllers in a multiprocessor. Cache must recognize when a line that it holds is shared with others. When an update action is performed in shared cache line, it must be announced to all the other caches by a broadcast mechanism. So each cache controller is able to, quote, snoop on the network to observe these broadcast notifications and react accordingly. And so there's more details here. So there's two basic approaches, write and validate and write update. And so we have charts that look at each one of those separately. So when with a write and validate protocol, there can be multiple readers, but only one writer at a time. Initially, a line can be shared among several caches for reading purposes. When one of the caches wants to form a write to the line, it first issues a notice that invalidates that line to the other caches, making the line exclusive to the writing cache. And so thus you're saying it's only me that can do it. You got to wait for me to finish writing, and then you can pass it on to somebody else. With a write update protocol, there can be multiple writers as well as multiple readers. When a processor wishes to update a shared line, the word to be updated is distributed to all others, and caching contains that line can update. And so there's more details there, but it just gives you a sense of each one of those. Well, there's something called this MISHI protocol. And so this is stands for modifying, exclusive, shared, and invalid. And so these are the four possible states. And in a couple of slides, I'll show you some state diagrams. Maybe some of you have seen some of those before, maybe you haven't. And so to provide cache consistency on a SMP, this was one of the architectures I mentioned a few slides ago. The Dash cache supports a protocol known as MISHI, and these are the four possible states that are there. So this table summarizes the meaning of these four states. And so you can get a chance to be looking over that. And so this is some more details that are interesting to get a chance to be thinking about. So in this figure, it displays a state diagram for the MISHI protocol. Keep in mind that each line of the cache has its own state bits and therefore its own realization of the state diagram. And so in part A, it shows the transition that occurs due to the action initiated by the processor attached to the cache. And in B, it shows the transitions that occur due to the events that are snooped on the common bus. And so there's more details that you can read up on, but just trying to give you a better sense of that. So this figure summarizes the state relationship between lines in different caches, all of which map to the same block of memory. And so that's just some more details to give you some perspective. When a read miss occurs in the local cache, the processor initiates a memory read to read the line of main memory containing the missing address. The processor inserts a signal on the bus that alerts all other processors and cache units to snoop the transition. And there are a variety of outcomes that can take place. And so that is some details that are developed in installing. If one other cache has a clean copy, the other line in the exclusive state, it returns a signal indicating that it shares this line. If one or more caches have a clean copy of the line in the shared state, each of them signal that it shares a line. So if I got some good data, I want to make sure I tell all the other folks. If one other cache has a modified copy of the line, then that cache blocks the memory read and provides a line to the requesting cache over a shared bus. If no other cache has a copy of the line, then no signals are required. And so those are some things in terms of a read miss. So you can see there's a lot of bookkeeping that needs to take place. When a read hit occurs on a line currently in the local cache, the processor simply reads the required item. There's no state change. The state remains modified, shared, or exclusive. We also have the write miss. When a write miss occurs in a local cache, the processor initiates a memory read to read the line of the main memory containing the missing address. For the purpose, the processor issues a signal on the bus that means read with intent to modify. You see that when the line is loaded, it immediately marks modified. And so there's some more details that are spelled out with respect to other caches. Two possible scenarios predict the load of the line of data. Some other cache may have a modified copy, and no other cache has a modified copy of the requested line. For a write hit, when a write hit occurs on a line currently in the local cache, the effect depends on the current state of that line. So going back to the MISHI, and so we have a shared scenario, an exclusive scenario, or a modified scenario. And so we can see all that laid out here that you can review in more detail if you would like later on. So this is just some block diagrams that show the initiator read from write back cache. And so I think I'm just going to skip over this for right now, other than just give a high-level thought or two on this. It will help to clarify the state transition diagram that we showed before to develop flow charts that show the exchange of signals between cooperating cache during a read or write operation. And so this flow chart assumes an initiator system and one or more other participants referred to the state of a cache line in each system that map to the same block of main memory. And so here is the first of two block diagrams. This is for an initiator read from write back cache. And this is initiator writes to a write back cache. And so we have some information on both of those laid out. So we also have multi-threading and chip multiprocessors. Processor performance can be measured by the rate at which it executes instructions. And so we can be thinking of MIPS, million of instructions per second. And so the processor clock frequency, and the IPC, which is the average instructions per cycle. So we've talked about different types of measures of performance, but this is one way to be doing it. Increase performance by increasing the clock frequency and increasing instructions that complete during the cycle. And so you can see how when we were trying to have multiple chapters that we talked about how we could be increasing the average instructions per cycle, trying to keep that pipeline full, that is something. And also increasing the clock frequency, we're getting to a point where that's getting harder and harder to do. So having more strategies on this side is a possibility that can help. And so when we're talking about multiple processors, and we're not just thinking inside of a single computer, now we can be thinking of multi-threading. And so it allows for a high degree of instruction level parallelisms. And instruction streams is divided into several smaller streams known as threads. And so we can have these layers of breaking things down into, maybe if you want to think of it in terms of packetizing that as a flow. So maybe we should spend a little time talking about threads and processes and define them. And so a process is an instance of a program running on a computer. A process embodies two key characteristics: resource ownership. Process includes a virtual address space to hold the process image. The process image is a collection of program data, stack, and attributes that define the process. There's also the schedule and execution. The execution of the process follows an execution path through one or more programs. This execution may be interleaved with that of other processors. And so there's some interesting details that come up with that. A thread is a dispatchable unit of work within a process. It includes a processor context and its own data area for a stack. A thread executes sequentially and is interruptible so that the processor can turn to another thread. You can also have a thread switch. It's the act of switching process, the act of switching processor control from one thread to another. Okay, working on this thread, I'm working on another. There needs to have a way to make sure that that's clearly conveyed. You can have implicit or explicit multi-threading. So all of the commercial processors and most of the experimental processors so far have used explicit multi-threading. These systems concurrently execute instructions from different explicit threads, either by interleaving instructions from different threads or sharing pipelines or by parallel execution on parallel pipelines. Implicit multi-threading refers to a concurrent execution of multiple threads extracted from a single sequential program. These implicit threads may be defined either statically by the compiler or dynamically by the hardware. And so some more interesting details to be thinking about how we're going to be using multiple processing elements together to make things work better. So the majority is now in this explicit multi-threading mode. And so what are the approaches to explicit multi-threading? We can have interleaved, we can have blocked, we can have simultaneous, and we can have chip multiprocessing. All of these are possible. So for interleaved, this is also known as fine-grained multi-threading. The processor deals with two or more threads context at a time, switching from one thread to another at each clock cycle. You can have blocked multi-threading. This is also known as coarse-grained multi-threading. And the instruction of a thread are executed successfully until an event occurs that may cause delay, such as a cache miss. There's also simultaneous, and instructions are simultaneously issued from multiple threads to execute units at a super of a superscalar processor. And finally, we have chip multiprocessing. In this case, the entire processor is replicated on a single chip, and each processor handles threads. And so that is a possibility. Well, this is a complicated diagram. We could spend a lot of time talking about approaches to executing multiple threads. And so we can start from fairly simple over here and start to me thinking about the things like superscalar approaches that we've talked about already, and then start to introduce how we could include multi-threading. And so we can be going from fairly simple to more and more complicated, and then mapping out from each one of these point of view. So time goes down, and then things that are done in parallel go horizontal. And so we can just see that there's a lot of different possibilities that are there. So when I was reviewing this chapter, the thing that caught my attention, since there's been a couple of times that I've used cluster computers, and actually put in a picture here to maybe give you a physical representation of what it might look like. And so clusters are an alternative to SMP as an approach to provide high performance and high availability. It's particularly attractive for server applications. If I didn't tell you this was a cluster, you would just think this was a bunch of servers in a data center. And so it's defined as a group of interconnected whole computers working together as a unified computing resource that can create the illusion of being one machine. And when I've logged into a cluster, it looks like you're just logging into a single computer. And so the term whole computer means a system that can run on its own apart from the cluster. So I could pull out one of these rack-mounted computers and run whatever I want on it. I just have to reconfigure the software. So each computer as a cluster is called a node. And so the benefits, there's absolute scalability, incremental scalability, high availability, and superior price per performance. And so you have commercial off-the-shelf hardware, and so you can get things at a unit cost that would be fairly affordable. So here are some clustering possibilities. You have each one that has its own memory, and then you just hook it together with high-speed messaging links, or you have also some shared memory. And so they have individual memories, but there's also a RAID. Remember, we talked about this concept of a RAID. You're increasing the integrity of this by having various forms of redundancy to help its performance. So this is just talks about some of the benefits and limitations for each type of clustering approach. You can go ahead and review that in more detail, but I'm not going to spend too much time right now to focus on that chart. We also had with our taxonomy graph this non-uniform memory access. And so it's an alternative to SMP and clustering. And so we can either have uniform memory access, non-uniform memory access, or cache coherent non-uniform memory access. And so this is a detail that I'll just leave for you that you can review in installing, just to give just wanted to conclude to be thinking about that. So what is the motivation? With an SMP system, there is a practical limit to the number of processors that can be used, and an effective cache scheme reduces the bus traffic between any one processor and main memory. As the number of processors increases, the bus traffic also increases. So the objective with NUMA is to maintain a transparent system-wide memory while permitting multiple multi-processor nodes, each with its own bus or internally interconnect systems. So that's just some more details that you can be thinking about. Here is a graphic showing an example of some CC NUMA organization. So there are multiple independent nodes, each of which is in effect an SMP organization. And then there's some pros and cons. The main advantage of a CC NUMA system is that it can deliver effective performance of higher levels of parallelisms than SMP without requiring major software changes. And so those are some things that you can be thinking about. But like with everything, there are pros and cons for each possibility. So we've talked about a lot of different types of architectures here, and I won't go over the summary chart again, but I'll just finish up this lecture by just going back to this taxonomy chart. And so in this lecture, we try to give a little bit of insight to each one of these parallel processor architectures, which is the focus of what we're trying to cover with this chapter. Okay, I'm going to go ahead and end this this overview, and I'll stop sharing my screen, and I'll turn it over and see who would like to share their project. I look forward to seeing some of the great work that you all have been doing.
I left my kid at home. I thought I was in the car, so I'm currently at school right now.
Okay. Well, I'll come back to you, David, and maybe you might want to give a few words, introductions, but is there anyone else that would like to share about their project?
I can go first. I'll share one
Okay,
of the things with the Arduino, right?
Yeah, that'd be great.
So the video is on my phone. I can't really show it, but I have I used the fan thing that came with the kit, and it is like a motorized fan that you can sort of plug into the breadboard, and then I wired it up to a button. So whenever you click the button, it like turns on. So that was pretty much the most complex thing that I have so far. There's like 4 or 5 or 6 wires or so. I was gonna try and use a 7-segment display, but I couldn't quite get it to work because my coding skills are lackluster. But I got the fan to work.
Well, first I want to say, Enzo, congratulations on that. And so the number of times I've taught this course, so far no one has actually used a fan. So I'd be interested, and I'll look forward to seeing more of the details of what you have to get some better insight. And if you do have it set up on Thursday, that will be another chance you can give us some insight into what you uncovered. But why don't you just go just a little bit more detail about so you had the fan, and so you can connect with the fan. I don't know if there's any acknowledgement that the fan is sending back to the Arduino, or literally you're just watching the fan and you're seeing you can maybe have it go slow, medium, and fast. Or what were some of the things that you were able to see with your engagement with your fan?
As of right now, it's pretty much, well, I had 2 circuits. One of them, the fan was just constantly on, and then the other one I wanted to make it a little more complex, so I hooked it up to a button. I've not been able to control fan speed or anything yet, but there was another iteration of the circuit where if I plugged it in a different way to different pin outs, it would like pulse between on and off. So there is that, but I've not been able to go into the code and adjust fan speed. I've not figured out how to do that.
Well, that's fine, Enzo. I'm sorry if I'm going down a rabbit hole in one thing that I was thinking about, but turning it on and off, and now have the ability to control that with a switch. You can be thinking about like the Internet of Things. There's various analogies. Just one that comes off the top of my head is like you can have like a microcontroller for your home HVAC, heating and air conditioning. And so you can turn it on. You can either turn on or off the heat or the air conditioning. And so you've got some basic functionality of a physical thing that you're controlling with your Arduino. And so you could argue that the interface, the way you actually had 2 ways to be doing it. You could have through the Arduino from your computer, you can command it on and off. And so that would be like, say, like a remote way of controlling it, or you can have the push button method. And so we're getting a chance to get some insight into a couple ways of thinking about a cyber physical. With it, this third project, we're focusing bringing in this live input and output, this I/O part of the Vinomer architecture. And we're also having some programming, and we're seeing how we can do some of the programming in software and some of it in the hardware, and having this interesting partnership between those. All right, well, thank you, Enzo.
Yeah, thank you.
Anyone else like to share about their project?
I can share mine.
Sure, go ahead, Isabel. I said it so people can share their screen, so feel free to do that.
Well, I have it set up right now. Is it okay if I turn on my camera and just show it?
Yeah, either way.
Oh, I'm trying to figure that out. Okay, hold on. I don't know how to flip the camera, but I'll show you. So this is my Arduino. So it has 3 different buttons: rock, paper, scissors.
Uh-huh.
And in the code, it has a random number generator. So when I upload, the computer would choose something, and you go ahead and pick whichever input you want. So let's say I choose rock, I lose because the computer chose 1, so he chose paper. So if you would have pressed paper, it would have been both on, meaning you got a tie. And if you chose scissors, you would have won. So that's my project.
Well, that's really wonderful. Congratulations, Isabel. Maybe you wanted to share a little bit about you've experienced it, I'm sure, with software, but now you've experienced it doing some hardware. What did it feel like to actually get it to work?
It took me a while to figure out the wiring, because I didn't understand. Like, I never done breadboarding. So I even phoned a friend just so like I can get a better explanation. So I learned that everything works in columns and rows, and I was able to like do one button. And once I was able to do one button, like getting it to work, I did the 3. And then from there, I messed around with the examples and the Arduino documentation, so I can see the LEDs as well. And once I was able to like figure out the wiring, I was able to duplicate it and do it how I want. And the programming was fairly easy. So the main part that I spent like time on was the breadboarding.
Well, thank you for that, Isabel. I remember a couple months ago when I was just encouraging you just to pull it out and start to put things into your breadboard and stuff like that. So so congratulations. Now you can say you've actually built hardware.
Yay.
So that's something that you could be putting on your resume, that you've actually done programming and configuring with Arduino kits. And so I always like to have people think about, when you're doing a resume, it's really, you want to be, quote, bragging about yourself. You want to be giving the person that's reading your resume the best sense of who you are and your capabilities and your experience. And so you're in school, but you're also getting some experience. And that's one of the reasons why I like to have project work in my classes. So thank you, Isabel. Anyone else wants to share their project? Okay, well, this is time for you all. So it's up to you whether or not you want to be doing this. I will allow some time on Thursday as well. So let me just do a last call. Anyone wants to either talk about their project or share their project? Okay, well, I look forward to seeing you all on Thursday. If anyone does have any questions, please feel free. Let me just mention a few other details. Next week, we will have a final. And what I'm planning to do is make it a take-home final. It will be administered through Canvas. There's an access code that I will be providing via email. You can only take it on the day of the final. It's not something that you're supposed to share, and it's only a single time that you can be doing that. And so also make sure that you get all your, some have missing assignments that they still need to complete. So please be diligent and complete things that you haven't done. I'm very happy to give people credit for work. And with that, I'll look forward to seeing you all on Thursday. Okay, God bless now.
Thank you.
Thank you. Have a good one.
I have
Thank
one
you.
question.
Yeah, sure.
It's regarding the faith integration essay. We
Yes.
talked about it a little bit last week. I guess I just want a bit more clarification on what that is meant to entail.
Yeah, I updated, I had a couple folks ask me about that. And I hadn't actually put anything in the text, and so I actually provided some more details. And so if you open it up, you can see it, but I'll also put it here in the chat. Let me see. I'm not sure what happened. Let me try that again.
Okay, yeah, I see that it has a lot more details now.
I think instead of doing what I wanted to do, I just put on CC. So let me try and get rid of this. Okay, well, I'm sorry if there's gonna be a CC. I'll just worry about that later. Thank you, Ryan. I hope you got another kid, and I hope that's working better for you. So
It comes in later tonight.
okay,
Well,
well, just keep me updated.
I'll see
okay?
if it works, and even if it does, I'm not sure if I'll even have enough time to make a project with it.
Well, I would recommend that you do that, Ryan. We've had all semester, and you know how to get in touch with me. Okay.
I know.
All right. Take care, Ryan.
Okay.
Any questions, Avery? Okay, I'll just assume we are having some comm problems. I hope you have a good day. Take care. Bye-bye.